Hello and welcome to the session FEM analysis of the First Steps course. Here you will learn how to set up a FEM model and how to analyze it. You will define boundary conditions for a cantilever beam which has a restraint and a force acting on it, and then analyze the deformation. This will help you to understand the structure of the individual steps of a FEM setup and how to assemble a runnable model. We need 4 different inputs for this lesson. One is the design space of the cantilever beam, which is a solid body, and if you would like to know how to generate solid bodies or geometry in general, please go to the geometry generation lesson of the First Steps course. Then also we have these non-design spaces as an input prepared, and then we have 2 surfaces, one which the force will be applied to, here the front surface of the non-design space, and another one which will be fixed or supported, which is here this surface. To build up a FEM model and then analyze it, we have to first create solid parts, then define RBE elements, define the FE boundary conditions, and then lastly we can assemble and run the model. So we have 4 steps to go through. Let's start with the first one and look into the solid part creation. A solid part is a fusion of a mesh with material properties. And first we have to mesh the solid body. And in this case we have 2 inputs, the design space and the non-design spaces. So our input is a list of solid bodies, which you know because of this dotted line indicating it. And now we have to mesh our solid bodies using the Altair hypermesh mesher. Type in solid mesh and you will get this component. Let's move it up a bit. And here you plug in the element size, also plug it into the minimum and maximum of interior size so that we get equally sized elements inside and outside, on the surface and also on the inside of the element. And then I would like to change the element type to quartz strictly, so that we only have quartz cells. And now this whole thing has to recalculate, of course. You can use the drop down for different settings, and you'd use it again, and now we have a strictly quad solid mesh. In case you don't have an Altair license, you can use this internalized model and just use this for the next steps. Okay, now we have our solid meshes, and right now we have, let's plug in a panel here to check what we have. As you can see, we have 3 different meshes. The first one is the design space and then the 2 non-design spaces. And to now define the solid parts, I would like to split up this list because I want to define the solid parts for the design space and the non-design spaces separately. So I will use the split list component. Plug this in here and we will split it after the first index. So now we have a single data value flowing through here, which is the mesh of the design space. And then we have 2 solid meshes in here. You can of course connect a panel to check. Yeah, this is 1 mesh and here we have 2 meshes. Okay, great. This is what we are going for. So now we can actually create the solid parts. Okay. If you type in solid part, you get this component. You can just copy and paste it. So we need it 2 times. You can connect the names, and then use the list A, which was the design space, solid mesh for this, and list B, which are the non-design space solid meshes for this solid part, and they both have the same material, which is steel. Just plug the material in here, and now we have two different solid parts defined. Just plug them into these outputs, and we are already done with our first steps. One more thing to know about the material: it's provided for you, so you don't need to worry about it at all, but it's important to know generally when you work on your own that the software is unitless, so you have to take care of what units your parts are in and adjust your values, for example materials, for those units. Let's continue to our second step, which is defining the RBE elements. Blend out the solid parts first. Alright, so we have this point here. Here you can see it. And this surface body, which is the front surface of the non-design space. I blend in the cantilever beam again so we can actually tell where we are in the model. Okay, so this is the surface and this is the point. And now we want to couple all nodes that lay within the surface to the point with rigid elements, and then later we will apply force to that point, but right now we just want to define those rigid elements that will couple the nodes to the point. So type in RBE and you will get the connector spider. You can of course also type in connector spider. We will name them force because we will later apply force to that point, and then define the target. As you can see right now, the component already works. We don't have to apply this point into the start node because right now the start node is the center of the target geometry. So this point here, oops, that point right now is our start node, and if I now plug in the provided point, you see that this now is our start node. And then we already have defined our elements. I will blend these out, and we can continue to the next step, which is defining the FE boundary conditions. At this point, we don't need a solid part or a mesh or nodes or anything. The definition of our boundary condition is purely geometrical, and later in the assemble model, those nodes will be selected. So let's start with the force I already talked about. We want to apply it to the start node of those connector elements. And I also prepared a vector here, which has a factor of 1000 and points in negative z direction. So I will just type in force to get the force component on the canvas and connect all the inputs. Okay, lastly, we plug in the vector, and as you can see, we defined our force. All right. So now we also have to define a support, because right now our model would behave like in space and just float off in negative z direction, because this is where the force is pointing to. So now we want to support our model and fix this surface. If you get the support component, give it a name, enter the support surface, again a tolerance, and now we have defined that all nodes that lay within this surface or within the tolerance to the surface of the model will be fixed in all 6 degrees of freedom. You can use these toggles here to select or deselect degrees of freedom. And now we have a force and a support, and these are 2 loads, which we will now combine together into a load step. The load step can be used for a static mechanical simulation, and we will give it a name. It's called load step. Plug in both loads, and now we have defined our load step and already finished step 3 of the FEM setup. We are now ready for the last step of this lesson, which is running the FE setup. And before we can do that, of course, we have to first assemble or construct the FE model. And for that, we need the construct model component. We plug in the name of this model, then the different parts, the rigid connector elements, our load steps, and you could also define a tolerance. So all nodes within this tolerance would be merged. In our case, we don't need a tolerance. Yes, so now you can see already we have our model defined here. And here you can now see the connector elements being displayed. And now if you are not happy with the location of the start node, you can go back to the RBE element section, blend in that start node, select it in the viewer and drag it to a different location. Alright, let's go back to our 4th step. So here we have now our model defined. If you don't have an Altair license available, here is an internalized model which you can use for the next step. So now we will actually run the model. However, you could also use this constructed model for a topology optimization, for example. And if you drag this wire, you get the OptiStruct solver suggested, and now this is running. It's an external solver that's running through, and the result is our FEM model, the load steps, and how the model responds to the loads. If you plug the successful output in here, you read true, which means our calculation has been successful. If there's an error or a warning, you will not get true, but probably false, and then you can also read about what the issues are if you plug in the info output into the panel. Before we will take a look at the model with the model view component, I will just press Ctrl A to select everything and hide everything selected so that we don't have different parts showing in the viewer. Okay, so let's connect the model into the model view. And as you can see, it runs through and gives us this nice look at the cantilever beam. And here you have lots and lots of settings to choose from to adjust this view. So right now we are looking at the load step and the element stress. We can also check out the nodal displacement instead. Then we can only look at the displacement in one direction, or we go with the magnitude of the displacement. Also, there's a displacement scale which I set to the maximum because it makes it easier to actually see something, but of course you can go with a more realistic view. And then also here you have the result bound for this color scheme, where your color scheme bound starts and end can be defined here. And then also you can choose from different color maps. I like the rainbow one. Then we have this easy luminant, cool to warm. This is yeah, very much a personal preference. Okay. And then also here you can go into the legend type, have no legend, discrete legend. Yeah, change the number of colors, change the font size, change the decimal places, the significant places. Very much, yeah, adapt this to your personal needs and how you prefer to look at your results. Okay. And now if we go back again, you could select our point here again, the start node, and if you now drag it to a different location, I am going with a more drastic change here, the whole DNA will recalculate. We are now already at the solver, and then you will be able to see the updated model view. In this session, we went through all the steps that are needed to set up a FEM model and analyze it in our software. You are now able to take this knowledge and transfer it to analyze your own products.